Sheila, as you already introduced, so today I'll be presenting on multi-classification of CAD entities, where we see like leveraging the entity as node approach with graph neural networks. And coming to agenda, like I would like to introduce what are CAD floor plans, what are GNNs, and what are the main contributions of this research work, and what is a workflow of GNN based CAD entity multi-classification, about the data set that we have used and the methods proposed for conversion of CAD floor plans to graphs and the proposed approaches. And finally we discuss about the experiment and results, finally conclude with limitations and like future research scope. So coming to CAD floor plans, CAD floor plans are nothing but we have the floor plans, like computer aided design floor plans of the buildings, and we have used like BIM, which is like building information modeling, which allows for enriched representation, where we have like the physical and functional characteristics of buildings. So in these floor plans you have all objects like they are depicted using these geometrical entities, which we call like you can see the lines and arcs, circles in a CAD floor plan, and these are nothing but geometrical entities. And we have explored these entities using graph neural networks so that we could exploit the maximal structural properties of these like drawings. And then by representing these CAD floor plans as graphs, we could also understand the relations between different entities, because we have the edges between the entities too. And then what are graph neural networks? So if you represent the data as a graph, which is like set of nodes and edges, you call that as a graph, and it is used to actually represent like complex data structures. And then we represent these CAD floor plans as graphs, and then we have used like 5 different like GNN architectures, which is like graph attention network, and we have the graph attention network version 2, and then like generalized aggregation networks, principal neighborhood aggregation, and then unified message passing. And then so there are different scenarios where you use graph neural networks. For example, you have to classify each node in a graph, or you want to classify the edges in a graph, or you want to classify whole graph as itself. And here we are dealing with the node classification problem, where we want to just classify each node in a graph. And what are the main contributions of my research work? So I have used these graph neural networks in order to enhance these vector representation of CAD floor plan elements. And I have used intersection based element split, and then I have applied like multi-class framework to this classification. Like I classify these entities as walls, windows, stairs, doors, and others. Like if something that's unknown, it's classified like miscellaneous. And then finally leveraging like edge based entity relations, so we also used like edge features in order to improve the entity classification for this problem. And coming to the workflow that we proposed for this CAD entity multi-classification, you could see in the image there is input CAD floor plan. This is how it looks like. It has like windows, stairs, walls, and doors represented, and we converted this into graph representation, where each entity is represented as one node in the graph. And then you have the edges between the nodes, and we will discuss in the like in further slides how we have connected edges between these entities, or what we call as nodes. And then once we have the graph representation, we feed this information to graph neural network, and finally we train the like graph neural network. And then we have final like multi-classification, where you can see in the semantic graph representation, which represents the stairs in different colors, like windows in purple and wall in green, which you could see here, and then doors in red color, and miscellaneous like in black. And finally, we have mapped this flow plan, like the semantic graph representation, like the prediction, onto the original flow plan, and you could see the exact visualization. And then next, coming to, yeah, what are the features that we have used in from these nodes. So each node in a graph has like 5 different features. Like for example, it has like what is a class, and what like fill, stroke, and style, fill opacity, stroke width, and stroke opacity. So these are the different features which are available in these CAD flow plans, like which we call like structural properties. And we have used these for as features for like training graph neural networks. And then coming to what is a data set. So we use like Cubicasa data set, and it is a publicly available data set, and you can see here the sample images from the Cubicasa data set, and it has around like 5,000 samples, and they are in SVG format. And we have used like almost 4,200 for training, and 400 and 400 for like testing and validation. Then coming to what are the different methods that I have used for converting the CAD flow plan to graphs. So I have used like 2 different methods, which is like start endpoint based connection, and another one is like intersection based split. So what is start endpoint based connection? So you have in the image you could see like entity A is nothing but you can see a red line which is called entity A, and you have another entity B and another entity C. So this, for example, this is like a simple example which elaborates like how we form the edges between the entities. And now I want to convert this to a graph and have edges between the entities. So in this method we represent each entity as a node. So here entity A is represented by a red dot, which is node A. And like entity B is represented in blue, and then entity C by green. And then now if we want to form edge between these nodes, and we see like if start point or end point of these entities are same, then we have an edge between them. And A and B have same starting points, so we have an edge between them. Whereas C doesn't have any start and end point, which is same with A and B. So therefore we don't have any edge connection between AC and BC. And coming to the intersection based connection, so here we just have the connection between the entities when there is an intersection between them. So C is intersecting A and B, therefore we have a connection between A and C and B and C. So this is the difference between these two methods. And coming to the edges, so you have entities and then you have edge features. So we connect what are the edge features that we take into account is nothing but, so you have an edge between an entity, and we take the maximum distance between the entities and minimum distance and the mean distance. So for now we have like used Euclidean distance in order to calculate this distance function. And then we just use these 3 different features like maximum, minimum, and mean distance. And then we use this as features while we are training the graph neural network. And then finally we have like 8 different approaches for classification of these CAD entities. And we name this approach as entity to node network, which is called ENNet. And then based on that we like we just categorize one approach as a baseline. And then we have like just like we have different approaches which are suffixed with D, C, and S, where we like which explain like what kind of an approach this is. So here you can see in the table like internet D is nothing but it uses like distance feature like between the edges. And you can see like it has, if the model has used intersection split, and what is the different like what are the node connection strategy used, if is it like start endpoint based method or intersection based method, and if it has used like distant edge features or not. So based on that we have like totally like 8 different approaches. And then so here it explains like what is D. It is nothing but we are using the distance between the nodes or not. And then C is nothing but we are like in which strategy like we have created the nodes. Is it based on intersection based method or start endpoint based method? And then finally we have like employment S, which is employment of crossing based subsplit, which is like if you have any duplicate like entities, we just remove one of them and we just use like intersection based subsplit. And then coming to the experiments and results, so we have used balance accuracy score in order to like measure the classification accuracy. So why have we used balanced accuracy? Because the data set like has it's imbalanced because the labels in the data set like are imbalanced. So we use this metric because it's proven like it's better metric for a class like imbalanced data set. And then how do you calculate this is like we use sensitivity, which is calculated from the true positives and the false negatives, and it measures like the proportion of factual positives which are identified by the model for a class every class, and we average this across all the classes, like the sensitivities across all the classes, and it gives the balanced accuracy metric. And then these are the results which we obtained from like 5 different graph neural networks and using the 8 different approaches. And as you can see from the table, like like the accuracy score in bold represents the maximum balanced accuracy across that column. And then we can see like using this intersection based subsplit and distance feature, we could see that there is an increase in the accuracy. And like you could see GANet has accuracy of 98%, where we have the connection which uses like distance metric and also connection based on intersections subsplit. And then UniMP model has an accuracy of almost 100%. Here you could see that the data set is not a very large data set, and this model could easily predict because the classes, even the classes which we use are almost like 5 different classes. So we almost achieve like 100% accuracy for this network using this approach. And then finally, like coming to conclusions, so we could say like we have proposed the like graph neural network based like multi-label flow plan entity classification method, and we have seen that using intersection based subsplit has enhanced the classification, and finally like removal of duplicate elements also has improved the classification. And we have used like sweep line technique, and we could see that it works only with straight line components and not with curved line elements. So we in future we could also find something which also works with curved line elements in a cat flow plan. And finally, like this could be as a novel approach which could be used for classifying the entities in CAD flow plans. But the method we have used for connecting the edges between the entities is like computationally expensive, because we compare like start end points of each entities to all the other entities in CAD flow plans, which is like computationally expensive, and we need to find a method which could make it very like computationally inexpensive. And further, like we would like to investigate what are the different node features which could be useful. For now we have limited to few features, so by adding extra features or finding other features which could be more helpful for this classification. And then in future we could also think of different edge features that could also be added instead of maximum minimum distance, so that we could classify, we could better represent the relations between entities. And yeah, so thank you for your attention.